So welcome, future machinists. So this is like the machine shop overview. I'm Ani, and my co-presenter is Damien. We are the managers for Machine Shop. I look at all the CNC and automatic machines while he looks at the manual machines. And our VP, Alex, is not here. He is elsewhere right now taking care of some personal matters. So Damien, would you feel like to start us off? I think your audio is not working, buddy.
Hear me?
Yes, I can hear you now.
That was weird. So, measuring tape plus ruler. Inches, like
Oh, my bad.
1/8.
Damien, could you speak a little more towards your microphone? We can faintly hear you.
Just in increments of 1/2, 1/4, 1/8, and 1. Caliper has a dial calipers, digital calipers. One dial caliper, mainly because digital are pretty. And measuring faces, they're outside, which.
Are we all having trouble hearing him?
Yes, it's very faint.
We probably need to change some settings on your computer or on Teams.
Okay.
Ani, I don't think you need to change any settings, just Damien.
Okay.
Which settings can I change?
Usually you can make some changes in your settings. What are you working on an iPad or a laptop?
Laptop.
Your laptop might have better speakers. It just might not be calibrated. But you can change your audio input. Are you running Windows 10?
Yeah, I'm running Windows 10.
So settings, let me see here. System, sound, input, and you can change your input and troubleshoot input. It might be easier just to talk through your laptop.
Better.
Test it one more time.
Okay, is this working better?
I can hear him better. How about you guys?
I can hear him better as well.
All right.
Okay, I guess we will just go with this.
Temporary fix. This will work. Go ahead.
Okay, so calipers. Calipers is digital dial vernier. We mainly use dial calipers because digital calipers are not very precise. Dial calipers are more precise. And measuring faces, so to measure on the outside, you use the lower jaws for external measurement. To measure the inside of an object, you can use the upper jaws, and you just put them inside the object and dial it out until it reaches the ends. And then depth, there's a depth rod at the very end of it. You just drop that down to the necessary depth. So it goes from left to right. So you can see here on the very left, there's increments of 1/10. Well, you can go first. It goes from inches, then it goes from 1/10 of an inch, and then on the dial it shows the second and third decimal places, tens and thousands places. So, yeah, so in this case, it's 1.438 because 1 inch. So it's past 1 inch, so it's 1 inch width. Then you go, it's past 0.4, so 1.4. And then the tick where it's at is 3.8, so it'd be 1.438, I think, in this case. Or 3.7.
Yes, there you go.
Yeah. It's a little tricky, but you'll get used to it with time. So in this case, I want you guys to see if you can find out the measurement for this one.
Just unmute yourself and blurt out the answer.
Yeah.
1.403. 2. Wait.
Okay.
Okay. Anyone else?
People?
$1.42.
So let's think about this here. You did the 1, right? Yes. And then you see it's in between 4 and 5, so that is 4. You have to first think about this as 0, 1, this is between 0 and 10, right? So would it be 2, 0 or 0, 2?
0, 2.
That's
0,
right.
2.
So what would it end up being?
1.402.
That's right.
Yeah. Okay, power tools. So first power tool we'll go over is the drill. It has drill bits measured in metric, imperial, or letter. We usually do imperial or letter, depends. And then for a drill, you can either go torque or speed. The number 1 setting on a drill is torque, and the number 2 setting is speed. Usually for drilling, it's good to go with torque. And then the rivet gun. So this is the pneumatic one. There's the battery is the one in the picture. Well, this one is a hand rivet gun with a battery. There are other ones where you need to plug it in. And this one, you just insert a ribbon at the front. You press down the hole and you hold the button and it will rivet it in for you. Okay, Dremel. So there are different tool heads. There's different ones for there's sanding drum, sanding band, sanding disc, and cutting wheel. Cutting wheel used for just cutting rods and other material, usually metal rods. And sanding drums and discs you can use for sanding down material with the Dremel. So hammers, mallets, and dead blows plus basic mechanical tools. So here's a hammer. So for structure, you always want to have your hand like right in the middle of the handle for less slippage. So when you're hammering, your hand doesn't slip around. And then the face is just where you strike the object, and the peen is the spherical face, which you can see on the ball peen hammer is just the round part. And there are different types of hammers. There's claw hammer, which is a standard one, just putting in nails and prying them out. Sledgehammer, it's more weight and you can put more force into it, but it's a bit hard to control. Then ball peen hammer, the ball peen is usually used for shaping metal. And mallets, nice thing about mallets is they will not deform the striking end as a metal hammer would. It has soft blows, so you don't have to worry about the metal you're hitting denting or anything. So you can. Then dead blows. These are just mallets filled with sand, and when you hit it down, normally when you hit down a mallet, it would bounce back up at you, which is not good. So dead blows, if you hit down a mallet, the sand keeps it from bouncing back up and more weight behind it.
So next, I'll take it from here. Screwdrivers. So we have 2 types of screwdrivers that we mainly use in robotics. there's the flathead screwdriver, which is, as you can see, these two pieces. So that's what we call flathead. And we have our Phillips head, which is this one, the standard one. Since we use mainly socket head screws, we don't really use these often. But when we, but in the case that we do, these are the two that we usually go to. So pliers. So you have obviously your different types of pliers. You have your flat nose type of pliers, and then you have, this is your flat nose, this is your needle nose, and then you have your flush cutters. All of them are used, well, the function of pliers, they're all still the same, but then all have different functions. This is more used for wiring, we could say, while when we use a rivet gun, there's some residuals that are left. That's where we use our flat nose pliers to get into like tight spaces. Our needle nose pliers are mainly used for screws, considering it's more like heavy duty and durable compared to the flat nose and the flush cutter. So wrenches. So there are types of wrenches. There's the hex key wrenches, which are these right here. These are very standard in your machine shop and just in robotics in general. If you're like a mechanical / fabrication person, you never go around the room without this. And so then you have your ratchet wrench. This is why it's called a ratchet wrench. So basically, when depending on the side that you were on, the way how you fasten a nut, if you do it the correct way, when you put a hex key on one side and then you put a nut, you can counteract the two motions and then just tighten it without having to turn your body too much. Because if you just bring the wrench back, it'll just make it like sort of a click, click, click sound. That means the nut is not moving, only your hand motion, which would result in the wrench moving. And then you have your crescent wrench. Looks like a big C. This is what's used to like grab a hold of a nut or a screw, let's say, and get a tight grip on it. And then Allen wrench is just another fancy way of saying hex key. Center punches. So there are two types of center punches that we use in robotics here. They're spring-loaded center punches. They're easier to use. All you have to do is just put it on the spot, put your other hand on top, and slam it onto the ground with your hand. But then like there's only like a small hole and dent, and generally you would like a big hole when you're trying to center punch. So that's why we use the manual one. So with the manual, it has a very, very sharp end, much more sharper than this spring-loaded one. And as you can see, there, we don't use our hands for these. We'd rather take a hammer and just hit it. That'll create a larger hole and a bigger dent, which will be much easier for us to use. So mechanical safety. After fabricating parts, you just don't go and give it to the assembly people. What we do here is deburr. What that basically means is take your sharp edges, sharp holes, etc., and debris, and you just clean it off. This is to ensure safety. Mechanical people are working with the metal, so they don't cut themselves, and blood splatters all over the place, and that just becomes a huge mess. So there are 4 things that we generally do in the shop. One is file. Files are used for edges. And then we would just rub it on an edge, and there you go. That's essentially like a smoothed out edge. We don't want it to be too sharp. Next, there's the swivel head deburring tool, or as we like to call it, the whirligig. So what that does is when we have large holes, specifically for like bearings, which I'll cover later on, we use that to clean up and sort of de-sharpen that hole so the bearing can go in smoothly. Next is a countersink deburr tool. That's this thing right here. Oh, and whirligig is this. So what we use the countersink is for like drilled holes. After we put a hole into a piece of metal, we like to countersink it. This ensures that it's like not too sharp of a hole, and like the edges are like easy for a screw to go in and out. And then finally, the laborious process of Scotch brighting. This is to get like a sort of smooth texture on the metal. Scotch brighting is actually very important because in some years we have decided to anodize our parts. What that basically means is it's like dipping it into black ink, sort of coats the metal, and the metal needs to be like fairly smooth and prepped for that. So that's where Scotch brighting comes place. arbor press. So the main use of an arbor press is applies a lot of force to push to push a part to push it into place. Basically, what that basically means is when we have our like metal bar, like a metal plate, we have bearings that need to be attached to it or like put into it. That's where the arbor press would come in. We would take like a sort of cylindrical type of material, put that and then align it to the bearing outside ridge. And then we take the arbor press and put this on a flat surface and then just put it in. That's the one way how we put bearings in. If you do the reverse by going to the other side of the part, let's say, and we do the same method, that would pop the bearing out. This is to ensure that one, the bearing comes out clean and doesn't go through lots of damages, and two, we keep the part intact while we're putting the bearing in or taking it out. Scribes. These are very important when it comes to fabrication because this is how we used to mark our metals. It's usually on plates for cutting areas or areas for drilling. Without a scribe, trust me, it's very hard. Using a marker just doesn't cut it because it's too thick. So scribes ensure that like we know exactly where we're cutting, and then we usually put like an X on the spot that we do not need. So that represents the side that we cut using the band. So I can explain that a little later. Next is the chain breaker. So they involve chains, obviously. That's why it's a chain breaker. Two things that it does is add chains together and removes the chain links to separate the change. This is just an example of a number 25 chain breaker or like a chain tool. There's also a number 35. Both are commonly used in FRC. These are mainly used for obviously chaining, and chains are used for our movement. Next, finally, the heart of this presentation, what machines we have in the shop. So we start off with the simple drill press, or I should say the humble drill press, sorry. So obviously it's used to make holes in parts, to simply drill holes and put holes in the metal. We mainly use this for prototyping, as with prototyping, you don't need as much precision as you would when a product has been finalized. And it's obviously more precise than hand drilling because it's a straight vertical motion. You don't have to deal with the hand moving or anything. If you can take a look at this like sort of spherical figure right here, that's what we use to bring this piece of metal down onto this vise where we have our plates on. And then obviously a screw goes in, I'm sorry, not a screw, a drill bit goes in over here, and that's what we use to make holes. Again, we use the scribe to mark where our holes are by drawing lines. And then obviously the connected points are where our holes are. Next is the shear. This is used to cut thin metals, and I emphasize thin. If you put like 1/4 inch material in there, it's not going to work, and we're going to get very mad. So the materials that it's mainly used to cut is 1/8 polycarb, 1/16 steel, and 1/16 aluminum. We use something called acrylic here. If you use acrylic on the shear, it will shatter, and that's a very sad moment because we like our acrylic to be non-shattered. But yes, never exceed these like rules. If you go and put 1/4 polycarb or like 1/8 steel or 1/8 aluminum, it's not going to be it's not going to be good in the end. You won't get your clean cut, and you might have a chance of like ruining the shear. Next is the finger breaker tool, or as I like to call it, the bender, because its use is it bends metal for us, or like material. Again, only use 1/8 aluminum or thinner, obviously, and 1/8 polycarb. And again, never bend acrylic; it shatters again. Acrylic is like non-malleable. So bandsaw, it's used to cut material, as the name of saw. So as you can see, this sort of gray sleeve over here, inside that is a very sharp blade that goes up after I hit the start button, which is right over here. It goes up and down. It goes up and down, and that's what we use to cut. So the types of materials that we use to cut is aluminum and plastics. As you can see, there's absolutely no wood. You should never cut wood with bandsaw. You should never cut steel with a bandsaw or G10. And for people who don't know what G10 is, it's a type of fiberglass. And obviously, when you're applying that much, when you're cutting with bandsaw, since two objects are in contact with each other and one's in motion, that causes friction. Friction then results in heat. So if you're cutting very small objects, like a standoff, if you would say, since it's a very small object, the heat can spread much quicker and you will burn your fingers very fast. This is something every machinist goes through. Don't be surprised if you have a burned finger. So next, so this is our second most used machine in the shop. This is the lathe. So it spins the part. The difference between the lathe and a mill, the lathe, it spins the part instead of the tool, while the mill, which I'll show in the next slide, it actually spins the tool rather than the part. So if you can look at this small circular area right about here, that's where your part goes. And then if you can see this vise over here, that's where your tool goes. So this can be dangerous. Obviously, there's some safety regulations, such as like if you're a girl and you're using the lathe, tie up your hair, and for all genders, just roll up your sleeves. Make sure you don't have anything on your wrists while doing it, and always have safety glasses on, and always have a spotter next to you, ready to hit the stop button. I'll go into operating the mill on a later presentation, mill and lathe on a later presentation. This is just an introduction of that. What we mainly use for the mill are for standoffs. These are just like cylindrical, not tubes, but filled in tubes. And then we have axles, which is just a pentagonal sort of shape. No, sorry, not pentagonal, hexagonal. And then we have rods. Again, it's just the same thing. It's like the similar material as standoff. And spacers. Spacers are used to create gaps in between our parts so that the metal doesn't rub off of each other. Finally, the Bridgeport mill. So majority of our parts are created on this. So this is more precise. So actually, no, not more precise, significantly more precise than the drill press. The materials that we use on this is aluminum, steel, plastics like polycarb, acrylic, Delrin. Everything you got it, we're going to put it on the mill. And this is by far our most frequently used machine in the shop. And Damien over there is a specialist on the mill. He works with the mill almost every day during season while I work with the lathe. So if you want stories, he has countless of great mill stories.
Yeah.
Finally, our newest machine and sort of the work in progress is the CNC. It's the computer numerical control. So unlike the other machines, which is manual, this is an automatic machine. What that means is if we feed it in a program and it does it for us. So what we use in order to, the program that we use is and we use CAM, which is computer aided machining. So we'd obviously CAD a part, we'd upload it to CAM, and then we'd do the necessary measures that need to be taken. And after that, we program it using Autodesk HSM. If you want to learn more about that, please contact Sadesh or me. So it's very similar to actually the Bridgeport mill. It's higher speed. It makes it easier to do more complex parts efficiently, and it's commonly used for cheesing parts. The term cheesing is used a lot, and it's a very simple thing. What cheesing does, it's basically we take a big plate, and then if we only need like 5 holes on it, we'll still have to take the entire plate's mass. What cheesing does is it makes like these triangular sort of holes around the part that would thus lower weight, and let's be honest, it looks pretty cool. Any questions? I know this was sort of just like an info dump, but as this like first semester goes, you'll be thoroughly shown what exactly each and every single machine can do. Each will have its own separate presentation other than the drill press and bandsaw, and like the other basic tools that can be all compiled into one. So do I have any last minute questions, or everyone sort of grasped at least a little bit in what Damien and I have presented today.
Yeah, any more questions, guys?
Let me ask one. So
Okay.
if you're doing the general fabrication process, what are the general steps? So you're receiving a drawing, right?
Yes.
Or something of the sort with specific specs and characteristics. And then what are your steps from there until delivery to assembly?
So, like Mr. Grady said, we get our drawing from CAD, which, like he said, has all our specs and stuff needed. The first thing that we actually do is get mentor approval on it. So whether that would be our head that would be our head mentor, Mr. D, or our fabrication mentor, JP. They have to put their signature on it before we start anything. Once we get the approval from them, that's when the process begins. They specify what thickness material we need. If it's aluminum, we use aluminum, etc., etc. We take it and then we use our scribe and like a ruler to measure out the exact measurements that we need with giving tolerance. What tolerance means is giving us a little extra room. So if I need to cut something into a 1 by 1, 1 inch by 1 inch, I would actually put it as 1.15 inch by 1.15 inch. What that does is when we take it to the bandsaw, because that's accounting for the thickness of the bandsaw blade. And we wouldn't want the bandsaw blade to take off what we need. That's why we give that extra leg room. And then from there, we take it to the respective machine that it needs to be on, whether it be the CNC or the lathe or the mill. And then if it's the mill, we hand program our specifications onto the system and have it run. And then if it's lathe, we take it to the lathe and just manually do it by the eye and the index that's given on the machine. And then if it's the CNC, we take the cam that was given, upload it onto the CNC, and then have it run from there. That's just the general process of this. And one thing I actually forgot to mention, when we're fabricating parts, always double the part that you're doing. So what that means is if I'm making 4 bars, it only says 4 bars, make 8. Because generally, excluding this season, obviously this season is special, we have 2 bots. One is our actual comp bot, and then the other one is a practice bot. So obviously, if one bot needs 4, the other bot also needs 4, because we like to keep a mirror image of each of the bots. So ask if they need 8, but generally you would need the double.
So you kind of spoke about the process between receiving the drawing and doing the actual fabrication, putting it in the machine, etc. Do you have any checklists for after that before it goes to assembly?
Yes. The checklist that mainly goes through is, did you deburr the part, as I said in a previous slide. That's the only checklist that we have. And then towards the end, we take one last measurement of the part to see if it meets the specifications that were given by the CADer.
Okay.
Oh, I have a question. Wait, like, what if like the piece needs to be a very specific measurement, and then you get it to that specific measurement, and then you deburr it, and then it's no longer that specific measurement anymore?
Well, usually deburring doesn't take off a significant amount of material, so you wouldn't have to worry about that. And there's
Okay.
also tolerance for each part.
Oh, okay. Okay. Thank you.
And in the engineering world, if I, as an engineer, received a part and it didn't meet the specs, I would expect some kind of analysis on why it's okay to use. And if it's not, I'm sending it back and I'm telling the manufacturer to do it again. I don't care how many times it takes.
That's how it usually goes, which is why our process before it actually comes to our manufacturer, us machinists, we make sure we check with CADers 20 times because we don't want to redo a part. One, that's a waste of time. Two, that's a waste of our resources that we have. And three, it's a waste of money because metal is expensive. Any other questions?
Nice work, you guys.
Perfect. So we have ended at 4:10. So if you, I don't know what the plan is after this. Damien, did you hear anything?
I didn't hear anything.
So welcome to your first day.
I can
Yes,
double
thank you,
check with Mr. Deep. From my understanding in the email I received, we are just breaking into these 4 groups. Let me double check the email and let you know if there's something else we need to do.
Perfect. Thank you.
Cool.
So this was day 1. Next week, we'll be diving deep into what each machine does. So starting off, we'll start off with the basic, what the drill press and bandsaw do, as that's part of a certification process that we require every single sub-team person to do, whether you're software, whether you're business, I don't care. You guys, you will get certified on the drill press, bandsaw, and hand tools. That's just a basic thing you need for robotics. While machinists specifically will get, after the whole initial process is done, machinists get certified on the mill and the lathe. CNC is a work in progress, as I said. I'm still understanding it as we go. It's a relatively new machine, and we've only utilized it, well, technically last season, but that's also this season.
Yeah.
Anything interesting you guys find?
Yeah.
How dangerous it is, I suppose.
It is
It does
fairly
get
dangerous.
dangerous.
Yeah.
I mean, you need to be careful. As long as you're careful.
Yeah.
Just don't touch
Damien and I have a good share of stories on that.
So if you do everything correctly and you follow all the proper checklists and steps, it shouldn't be dangerous. There is high risk, but as long as you follow those mitigation steps, there should be no danger to you at all. And that's why those steps are in place, and that's why we have the confidence to allow high schoolers and to do this kind of work without full professional training, right? It's just a quick kind of certification. I just got a message from Mr. Deep, and he says when we're finished, we can end the meeting, and that's it.
Okay.
Okay.
I will
I have
end
a
the
question.
recording.
Oh, okay.
Yes.
Do you need a certain amount of muscles to do fabrication?
No, you don't. The relative movement of each machine does not require muscle at all.
Yeah.
Although it does help.
It is a bit labor intensive, but you should be fine. You don't need a ton of muscle to do it. Anyone can do fabrication.
Rather than muscle, actually, you're going to need stamina and being able to last long hours in one room with only like 4 people in there.
Okay.
A good example, if you would like one, is during February we get this thing called winter break, and during that 1 week, machinists, we come in 10 a.m. in the morning, and then we usually get out of the shop by 5 p.m. or something like that, and then go back for like an hour, and then go back in from like 6 to 9.
Yeah. It is long hours that break because we're finishing all our parts.
So,
and those times when you're most exhausted and you're most tired and you've been doing it for long periods of time are those are the times that it's most important that you follow those checklists, because it's very easy to skip through, to become lazy, and that's when the real hazard and risk of being injured really comes up.
So there will be a lot of boba in the machine shop. I can vouch for that.
What about coffee?
There is coffee. So
Yeah,
if
there's
you get a
coffee.
chance to meet JP, he is an avid coffee lover. He at least chugs down 3 or 4 cups during our practice.
She said,
So-
let's skip the boba and go straight to coffee.
Straight to
Ah,
Sure.
Hey, anything that keeps us up.
Yeah.
How about good night's rest the day before?
Oh,
No, that's too far. Okay,
That's a
I'm
little
sorry.
too
I
far.
That's
didn't mean to
That's a
cross the
little
line.
too far.
All right. Do we have any more? Or are we all set?